Every space agency on Earth is lying to you. Not about whether we went to the moon. We did. Not about whether Mars is reachable. It is. They are lying about permanence. Every mission plan, every timeline, every breathless announcement about human settlements beyond Earth contains the same fatal flaw that no engineer will discuss publicly. The problem is not radiation. It is not distance. It is not money. The problem is launch cadence, the rate at which rockets must continuously leave Earth to sustain anything beyond low orbit. And when you calculate what permanent expansion actually requires, a terrifying truth emerges. Human civilization cannot maintain that cadence. Not now. Not in 50 years. Possibly not ever. If you are ready to understand why the stars may forever remain out of reach, hit that like button and subscribe. Now, get yourself nice and comfortable. Let's begin. The universe operates according to rules that care nothing for human ambition. Before any discussion of Mars colonies or asteroid mining or interstellar travel can begin, we must confront the fundamental physics that governs every attempt to leave our planet. These equations are not suggestions. They are not obstacles awaiting clever solutions. They are absolute constraints embedded in the fabric of reality itself, constraints that no amount of engineering brilliance or unlimited funding can circumvent. Earth holds everything on its surface with a gravitational grip that required 4.5 billion years of planetary formation to establish. Escaping this grip demands energy expenditure on scales that dwarf every other human endeavour. The escape velocity from our planet measures approximately 11 kilometers per second. Any object seeking to leave Earth permanently must accelerate to this speed or beyond while carrying everything needed for the journey ahead. Consider what 11 kilometers per second actually means in human terms. A bullet fired from a high-powered rifle travels roughly 1 kilometer per second. The fastest commercial aircraft cruise at approximately 250 meters per second. A Formula One racing car at maximum speed reaches around 100 meters per second. Reaching escape velocity requires accelerating to speeds 110 times faster than a racing car, 44 times faster than a jet aircraft, 11 times faster than a bullet. And this acceleration must occur while carrying passengers, life support systems, fuel, and everything else required for survival beyond our atmosphere. But escape velocity represents only the beginning of the problem confronting space travel. The true tyranny comes from a mathematical relationship discovered by a Russian schoolteacher named Konstantin Tsiolkovsky in 1897. Working in isolation from the scientific establishment, Tsiolkovsky derived an equation that has haunted spacecraft designers ever since. This rocket equation describes something deeply counterintuitive about the physics of propulsion in the vacuum of space. To understand the rocket equation, you must first understand how rockets work. Unlike aircraft that push against air or cars that push against roads, rockets operate by throwing mass in one direction to accelerate in the opposite direction. The mass they throw is exhaust gas produced by burning propellant. Newton's third law ensures that for every kilogram of exhaust expelled backward, the rocket gains forward momentum. This seems straightforward until you consider the implications. To make a rocket go faster, you need more propellant. But more propellant means more mass. More mass means you need even more propellant to accelerate that additional mass. And that additional propellant adds still more mass, requiring still more propellant. The relationship is not linear, but exponential. Small increases in required velocity demand enormous increases in propellant mass. The mathematics proves unforgiving. A rocket bound for low Earth orbit, the closest possible destination beyond our atmosphere, must carry approximately 9 times its payload mass in propellant. This means that for every kilogram you want to place in orbit, you must burn 9 kilograms of fuel. A mission to the moon requires carrying even more propellant to escape Earth's gravity well entirely, and then decelerate into lunar orbit. A mission to Mars demands fuel not just for departure, but for mid-course corrections, orbital insertion at Mars, and potentially landing and return. Each additional maneuver multiplies the fuel needed at launch by exponential factors that rapidly become staggering. The Saturn V rocket that carried Apollo astronauts to the Moon stands as the most powerful machine humanity has ever constructed. This vehicle towered 111 meters tall, roughly the height of a 36-story building. At launch, it weighed nearly 3 million kilograms, comparable to the weight of 400 adult elephants stacked together. Of that total mass, approximately 2,800,000 kilograms consisted entirely of propellant. The command module that actually reached lunar orbit and returned safely to Earth weighed roughly 5,500 kilograms. Pause to absorb what these numbers reveal. The ratio of launch mass to delivered payload exceeded 500 to 1. For every kilogram of spacecraft that touched the Moon and returned, over 500 kilograms of propellant burned during the journey. The engineering achievement of Apollo represented humanity's greatest technological triumph of the 20th century. Yet the physics of that achievement consumed resources at ratios that reveal the brutal economics underlying all space travel. Modern rockets have improved these ratios somewhat through better engine designs, lighter structural materials, and more efficient propellants. SpaceX's Falcon 9 can deliver approximately 23,000 kilograms to low Earth orbit from a launch mass exceeding 500,000 kilograms. The ratio has improved to roughly 22 to 1 for reaching orbit. The Starship system currently under development aims for even better performance through full vehicle reusability and advanced manufacturing techniques. But no chemical rocket can escape the exponential trap embedded in the rocket equation. The physics of combustion imposes fundamental limits on how much energy any chemical reaction can release per kilogram of propellant. The best liquid hydrogen and oxygen engines operate near the theoretical maximum efficiency for chemical propulsion. Incremental improvements remain possible, but revolutionary breakthroughs in chemical rocket performance do not. The mathematics has been understood for over a century, and that mathematics allows no exceptions. This brings us to the first uncomfortable truth about human expansion beyond Earth. Every kilogram of food, water, oxygen, medical supplies, replacement parts, scientific equipment, clothing, tools, and human beings that leaves our planet requires burning hundreds or thousands of kilograms of propellant. Sustaining any permanent presence in space demands a continuous flow of mass from Earth's surface into orbit and beyond. This flow cannot be interrupted without consequences. It cannot be reduced below minimum thresholds without catastrophe. It must continue day after day, month after month, year after year, for as long as any presence is maintained. The International Space Station provides the most sobering case study available for understanding what permanent space presence actually requires. This structure, orbiting approximately 400 kilometers above Earth, represents humanity's most ambitious attempt at sustained habitation beyond our atmosphere. Construction began in 1998 and continued for over a decade through dozens of assembly missions. The completed station masses roughly 420,000 kilograms, comparable to the weight of a fully loaded Boeing 747 aircraft. It supports a continuous crew of between 3 and 6 astronauts conducting scientific research in microgravity conditions. Maintaining this single outpost requires a launch cadence that most people dramatically underestimate. It cannot generate water from raw materials. It cannot produce the chemicals required for its life support systems. Everything the crew needs to survive must be launched from Earth's surface, travel through space, and dock successfully with the station. Confirmed records from space agencies worldwide show that the International Space Station receives approximately 8 to 12 resupply missions per year. These missions deliver food to feed the crew. They bring water and the chemicals needed to regenerate water from waste. They carry oxygen generation supplies and carbon dioxide scrubbing materials. They transport scientific experiments and return completed research to Earth. They deliver replacement parts for the dozens of systems that degrade and fail in the harsh space environment. They rotate crew members whose bodies cannot tolerate indefinite exposure to microgravity. They remove accumulated waste that would otherwise overwhelm station storage capacity. Each resupply mission represents far more than simply loading cargo onto a rocket. Each mission requires a dedicated launch vehicle manufactured through industrial processes spanning months. Each requires a cargo spacecraft designed, built, and integrated with station systems. Each demands mission control support from dozens of specialists, monitoring every phase of flight. Each necessitates extensive testing and verification before any vehicle approaches the station where human lives depend on perfect execution. Calculate what this means in terms of industrial commitment. Maintaining 6 humans in low Earth orbit, the closest possible destination beyond our atmosphere, requires nearly 1 rocket launch per month from Earth's surface. This cadence has been sustained since the year 2000, but sustaining it has required the combined efforts of multiple national space agencies representing the largest economies on Earth. The United States, Russia, Japan, Europe, and Canada have all contributed vehicles, funding, and expertise to maintain this single outpost in the cosmic ocean. The station itself cost over $150 billion to design, construct, and launch over more than 2 decades of effort. Its annual operating costs exceed $3 billion, consuming significant fractions of participating nations' space budgets. This staggering investment supports 6 people conducting scientific research in a location that commercial aircraft routinely fly higher than during transatlantic crossings. The station orbits only 400 kilometers up. The Moon sits nearly 1,000 times farther away. Mars lies over 500 times farther than the Moon. This escalation in distance reveals the core problem that every space agency understands but rarely discusses in public forums. Launch cadence, the rate at which rockets must leave Earth's surface, determines whether any space presence can be sustained. The term sounds technical and abstract, but its meaning is brutally concrete. Miss enough, scheduled launches and supplies run out. Miss enough supply runs and equipment fails. Miss enough equipment, replacements and habitats become uninhabitable. Miss enough maintenance cycles and structures break apart. The chain of consequences admits no exceptions and grants no pardons. Launch cadence collapse represents the fundamental barrier to human expansion beyond our immediate cosmic neighborhood. Not radiation, not distance, not cost, not political will. The rate at which industrial civilization can manufacture rockets, prepare launch facilities, produce propellant, train personnel, and execute missions creates an absolute ceiling on what space programs can accomplish. This ceiling cannot be raised indefinitely, regardless of funding levels or technological advances. Physical and industrial constraints impose limits that exist, whether acknowledged or ignored. The International Space Station has survived for over 2 decades because launch cadence has been maintained through extraordinary effort and international cooperation. When the American Space Shuttle program ended in 2011, alternative cargo vehicles were already operational or in advanced development. Russian Progress spacecraft continued delivering supplies, while commercial providers developed new capabilities. When Russian vehicles experienced problems due to manufacturing defects or political disruptions, American commercial providers increased their flight rates to compensate. The system maintained adequate cadence through redundancy, flexibility, and the overlapping capabilities of multiple nations. But this flexibility operates within strict limits that cannot be exceeded. Every launch vehicle in existence requires months of manufacturing time, using specialized facilities and skilled workers. Every launch pad requires weeks of preparation between flights to inspect systems, repair damage, load propellants, and verify safety. Every payload requires extensive integration and testing to ensure it will function after the violence of launch and the harsh environment of space. Every mission requires trained personnel who take years to develop the expertise necessary for critical operations. These constraints create a maximum sustainable cadence for any launch infrastructure. A single launch pad might support 12 to 20 launches per year under optimal conditions with experienced crews and reliable vehicles. Expanding beyond this rate requires building additional pads, training additional personnel, establishing additional manufacturing lines, and developing additional supply chains. Each expansion requires years of construction and billions of dollars in capital investment. The industrial base cannot be scaled overnight regardless of urgency. Current global launch capacity has recently exceeded 200 orbital launches per year from all providers worldwide. This number has increased dramatically from the roughly 90 launches per year that characterized the early 2010s. The increase resulted primarily from SpaceX's development of partially reusable rockets that reduced costs and increased flight rates. Additional contributions came from expanding Chinese launch capabilities and the emergence of new commercial providers in multiple countries. Yet even this expanded capacity barely supports current requirements while leaving minimal margin for the dramatic increases that expansion beyond Earth orbit would demand. Existing launch capacity serves communication, satellite deployment, navigation satellite constellations, military reconnaissance systems, scientific missions, space station support, commercial imaging services, and technology development programs. Every launch slot allocated to exploration reduces availability for other purposes. The capacity is not unlimited, and the demands upon it continue growing. Now extend this analysis to destinations beyond low Earth orbit. The Moon sits approximately 384,000 kilometers from Earth. Every kilogram of supplies sent to a lunar base must first escape Earth's gravity entirely, then travel across the void between worlds, then either land on the lunar surface or dock with an orbital station. The fuel requirements multiply at each stage of this journey. The complexity of operations increases correspondingly. The industrial burden grows in ways that approach exponential scaling. Confirmed NASA planning documents for the Artemis lunar program reveal the scope of this challenge with uncomfortable clarity. Establishing even minimal, sustainable lunar presence requires not one rocket system, but several working in concert. The Space Launch System carries crew and critical cargo on missions, requiring maximum performance. Commercial rockets deliver supplies and equipment on missions where cost efficiency matters more than capability. Lunar landers shuttle between orbit and the surface, requiring their own manufacturing pipelines and operational support. Each component of this architecture demands its own workforce, facilities, supply chains, and launch cadence. The Gateway space station, planned to orbit the Moon, will require regular resupply missions analogous to those supporting the International Space Station. But every mission to Gateway must travel nearly 1,000 times farther than missions to the current station. Fuel requirements increase accordingly, based on the rocket equation's exponential mathematics. Mission durations extend from hours to days. Complexity multiplies as distance removes the possibility of quick problem resolution or emergency return. The industrial burden of supporting Gateway substantially exceeds that of supporting the existing station, despite hosting fewer crew for shorter durations. Mars amplifies these challenges by orders of magnitude that strain comprehension. The red planet orbits the Sun at an average distance of 228 million kilometers, but its distance from Earth varies dramatically between approximately 55 million kilometers at closest approach and over 400 million kilometers when the planets sit on opposite sides of the Sun. Orbital mechanics means that efficient transfers between Earth and Mars require launching during specific windows when planetary positions align favorably. These windows open approximately every 26 months and remain available for only a few weeks before closing again. During favorable windows, the journey from Earth to Mars takes approximately 7 to 9 months depending on the specific trajectory chosen. This transit time eliminates any possibility of emergency resupply, a constraint whose full implications become apparent when calculating what permanent presence actually demands. NASA's Design Reference Architecture for Mars missions represents the most detailed public analysis of what reaching Mars actually requires. This document, developed over decades by engineers who understand the physics all too well, estimates that establishing even a minimal crewed surface presence requires launching approximately 1 million kilograms from Earth's surface per crew rotation. This mass includes transit vehicles to carry crew between planets. It includes landing systems to deliver personnel and cargo to the Martian surface. It includes surface habitats to shelter crew during their stay. It includes consumables, food, water, oxygen to sustain life. It includes scientific equipment to justify the mission's purpose. It includes return vehicles to bring crew home. Each element must be designed, manufactured, tested, launched, and integrated into a functioning system. Convert this mass requirement to launch numbers using vehicles that actually exist or are under development. Current heavy-lift rockets can deliver approximately 20 to 30,000 kilograms to low Earth orbit per launch. Delivering 1 million kilograms to orbit alone requires approximately 35 to 50 launches. But mass delivered to orbit must then be boosted toward Mars, requiring additional stages that consume propellant. This propellant itself must be launched. Orbital assembly of Mars-bound vehicles requires additional support missions. The actual number of Earth launches required for a single Mars crew rotation approaches 100 or more under realistic accounting. 100 launches per Mars mission. Launch windows opening every 26 months. Maintaining continuous presence requires overlapping missions with crews already on the surface, while replacement crews transit through space. Supporting infrastructure in Earth orbit and potentially lunar orbit demands its own cadence independent of Mars operations. The launch cadence required for permanent Mars habitation climbs into hundreds of launches per year dedicated solely to Mars support, while all other space activities continue requiring their own launch capacity. This reveals the core problem that underlies every discussion of human expansion beyond Earth. Current global launch capacity cannot support permanent presence on Mars, while simultaneously maintaining existing orbital infrastructure, continuing scientific exploration of the solar system, supporting commercial satellite operations, and meeting military requirements that governments consider essential. The industrial pipeline that produces rockets, the ground infrastructure that supports launches, the workforce that operates these systems, and the supply chains that feed materials into production all face absolute constraints. These constraints are not technical problems awaiting clever solutions. They are physical and industrial realities embedded in the nature of rocket propulsion and manufacturing capacity. The tyranny of the rocket equation ensures that reaching distant destinations requires enormous mass expenditure that no technology can eliminate. The complexity of rocket manufacturing ensures that production cannot scale infinitely regardless of demand. The requirements of launch infrastructure ensure that cadence faces hard ceilings imposed by physical facilities and trained personnel. Every space agency's long-term strategic plans assume that launch costs will decrease and cadence will increase over time. SpaceX's Starship program aims to reduce costs dramatically and increase flight rates substantially through full vehicle reusability and rapid pad turnaround. If Starship achieves its design goals of 150 metric tons to low Earth orbit with vehicle reusability, allowing launches every few weeks from a single vehicle, the economics of space access will improve significantly. Cost per kilogram delivered to orbit could decrease by factors of 10 or more compared to current expendable vehicles. But even revolutionary improvements in launch vehicle performance do not eliminate the fundamental cadence requirements for supplying distant outposts. Improved economics makes individual launches cheaper, not unnecessary. A Mars base still needs food, whether that food costs $10,000 per kilogram or $1,000 per kilogram to deliver. Equipment still fails whether replacement parts arrive on expensive rockets or affordable ones. The laws of physics do not negotiate discounts. If Starship works exactly as advertised, supporting Mars still requires massive numbers of launches. Maintaining lunar operations still demands regular cargo deliveries that consume vehicle availability and pad time. Operating orbital infrastructure still absorbs launch capacity that cannot be allocated elsewhere. The numbers improve with better vehicles, but they remain daunting under any realistic analysis. The physics of departure creates a bottleneck that no rocket design can eliminate entirely. Every kilogram humanity places beyond Earth requires burning propellant, manufactured through industrial processes, transported to launch facilities, loaded into vehicles, and consumed during flight. Every vehicle requires construction from materials mined from the Earth, refined through energy-intensive processes, fabricated into components, and assembled into functional systems. Every launch requires infrastructure maintained by skilled workers, operated according to demanding schedules, and protected from weather, accidents, and attacks. This bottleneck is launch cadence. It determines what humanity can accomplish in space with far more authority than vision statements, political speeches, or inspirational documentaries acknowledge. Understanding why this cadence cannot be sustained at the levels permanent expansion requires means examining what actually happens before any rocket leaves the ground. The physics of departure is brutal, but the industrial reality that supports departure may be even more constraining. The rocket equation ensures that escaping Earth's gravity demands enormous effort, but manufacturing the vehicles, preparing the facilities, producing the propellants, and training the personnel who make escape possible requires industrial capacity that took decades to develop and cannot be expanded by decree. The launch pad sees only the final seconds of a process that began years earlier across thousands of facilities spanning continents. That process, and its absolute limits, determines whether human expansion beyond the moon remains aspiration or becomes reality. Stand at any launch pad moments before liftoff, and you witness only the final seconds of a process that began years earlier across thousands of facilities spanning multiple continents. The gleaming rocket trembling on its supports represents the convergence of supply chains so complex that no single human being comprehends them entirely. The engineers who designed the engines know nothing about the metallurgy of the fasteners holding the structure together. The technicians who loaded the propellant have never seen the factories where guidance computers were assembled. The flight directors monitoring telemetry could not explain how the composite materials in the payload fairing were manufactured. This distributed complexity is not a flaw in the system. It represents the only way human civilization can produce machines capable of reaching space. No single organization possesses all the expertise required. No single facility contains all the necessary equipment. No single workforce masters all the relevant skills. Rocket manufacturing requires the coordinated output of an entire industrial civilization operating at peak capability. Understanding why launch cadence faces absolute limits requires following these supply chains backward from the pad to their origins. The journey reveals constraints that no amount of funding can eliminate, and timelines that no management pressure can compress. Physical reality governs every step, and physical reality does not negotiate. A single Falcon 9 rocket contains approximately 400,000 individual parts sourced from more than 1,000 suppliers scattered across dozens of countries. This number sounds abstract until you consider what it means for manufacturing. Each part must be designed to specification. Each must be manufactured to tolerance. Each must be inspected for defects. Each must be transported to integration facilities. Each must be assembled into larger systems. 400,000 opportunities for error. 400,000 potential failure points. 400,000 items requiring documentation, tracking, and quality verification. The logistics of managing this complexity consume enormous resources before any actual manufacturing begins. Procurement specialists negotiate contracts. Quality engineers audit supplier facilities. Logistics coordinators schedule deliveries. Paperwork alone requires dedicated teams working continuously throughout the production cycle. The first stage of a Falcon 9 incorporates 9 Merlin engines arranged in a circular pattern at the vehicle's base. Each engine contains approximately 50,000 components, manufactured to tolerances measured in thousandths of an inch. The turbo pumps that feed propellant into combustion chambers spin at over 30,000 revolutions per minute, while handling temperature extremes that would destroy ordinary machinery. Cryogenic liquid oxygen enters the pump at -183 degrees Celsius. Exhaust gases exit the combustion chamber at over 3,300 degrees Celsius. The pump must function flawlessly while experiencing both extremes simultaneously. These engines represent the most critical bottleneck in rocket manufacturing. No component better illustrates why launch cadence cannot scale infinitely than the rocket engine itself. Building one requires specialized alloys, unavailable from standard metal suppliers, manufacturing processes that take months to complete, and testing regimens that consume additional weeks before any engine can be certified for flight. The engine is where physics meets metallurgy, meets fluid dynamics, meets thermodynamics, and the intersection tolerates no compromises. The combustion chamber of a modern rocket engine experiences pressures ranging from 100 to over 300 atmospheres depending on engine design, while containing temperatures significantly higher than the melting point of any known structural material. Steel melts at approximately 1,400 degrees Celsius. The exhaust gases inside a rocket engine exceed twice that temperature. No material can survive direct exposure to these conditions for more than fractions of a second. Achieving sustained operation requires regenerative cooling, an engineering solution as elegant as it is demanding to manufacture. Cryogenic fuel flows through hundreds of tiny channels machined into the combustion chamber walls before injection into the combustion zone. As the fuel absorbs heat from the chamber walls, it simultaneously cools the structure and preheats itself for more efficient combustion. The fuel that would destroy the engine instead protects it, but only if every channel is manufactured perfectly. These cooling channels must be machined to tolerances measured in hundredths of a millimeter. A channel too narrow restricts fuel flow and allows hotspots to develop. A channel too wide reduces cooling efficiency below safe thresholds. The walls between channels must maintain precise thickness to conduct heat without weakening structurally. Manufacturing a single combustion chamber requires specialized computer-controlled machining centers that cost millions of dollars and take weeks to complete a single unit. Alternative manufacturing approaches using additive techniques, three-dimensional printing with metal powders, can produce some engine components more quickly. SpaceX has pioneered these methods for certain parts of the Raptor engine used in Starship. But additive manufacturing introduces its own constraints. The specialized printers cost millions of dollars each. The metal powders require careful handling and controlled atmospheres. Each printed part must be scanned and inspected for internal voids invisible to external examination. The technology accelerates some production steps while creating new bottlenecks elsewhere. Consider the supply chain for a single engine component, the injector plate that mixes fuel and oxidizer in precise ratios before combustion. This plate sits at the top of the combustion chamber and contains hundreds of precisely sized orifices arranged in carefully calculated patterns. Each orifice must be manufactured to within microns of specified dimensions. The pattern must distribute propellants evenly across the chamber to prevent destructive combustion instabilities. The plate material must withstand thermal cycling from cryogenic to combustion temperatures thousands of times without cracking, warping, or developing fatigue fractures. Testing a single injector design requires years of development and millions of dollars in prototype fabrication. Engineers build test articles, fire them on static stands, analyze the results, modify the design, and repeat the cycle dozens of times before achieving acceptable performance. A successful injector design represents accumulated knowledge from hundreds of failed attempts. This knowledge cannot be transferred through documents alone. It lives in the experience of engineers who spent years developing intuition for what works and what fails catastrophically. Confirmed industry analysis reveals that global rocket engine production capacity sits at approximately 400 to 500 engines per year across all manufacturers worldwide. This number has increased from roughly 200 engines per year in the early 2010s, driven by expanding commercial launch markets and government investment in new capabilities. But growth faces fundamental constraints that additional funding cannot rapidly overcome. The specialized workforce required for engine assembly takes 5 to 10 years to develop. A technician who welds combustion chamber components must master techniques that differ entirely from standard industrial welding. The thermal stresses, exotic materials, and precision requirements demand skills that cannot be taught in classrooms alone. Apprenticeship under experienced workers remains essential, but experienced workers are scarce precisely because the industry has historically been small. The testing infrastructure needed for engine certification requires massive capital investment concentrated in facilities that take years to construct. A rocket engine test stand must contain the explosive force of a bomb going off repeatedly while measuring performance parameters to high precision. The stand must supply cryogenic propellants at flow rates measured in thousands of kilograms per minute. It must capture exhaust gases safely and manage the acoustic energy that can damage structures kilometers away. Building such a facility requires environmental permits, construction timelines, and commissioning processes that span 3 to 7 years minimum. The supply chains for exotic materials face their own production limits, independent of engine manufacturing demand. Rhenium, a rare metal used in combustion chamber linings for its extreme heat resistance, has global annual production of only 50 to 60 metric tons. Rocket engines consume only a small fraction of this production, but dramatic increases in engine manufacturing would compete with other high-tech applications, including medical imaging equipment and petroleum refining catalysts. The mines producing rhenium cannot rapidly expand output regardless of price signals. Multiply this complexity across every major rocket component, and the scale of industrial constraint becomes apparent. Avionics systems that guide vehicles through flight require radiation-hardened electronics manufactured at specialized foundries with strictly limited capacity. Standard commercial semiconductors fail rapidly when exposed to the radiation environment of space. Cosmic rays and solar particles induce errors in memory chips and can permanently damage processors. Space-qualified electronics require special manufacturing processes that few facilities worldwide can perform, and those facilities serve military, intelligence, and commercial satellite customers in addition to launch vehicle manufacturers. Composite structures that form fuel tanks, payload fairings, and interstage sections require autoclave processing in facilities that cost hundreds of millions of dollars to construct. An autoclave is essentially a giant pressure cooker that cures composite materials under precisely controlled temperature and pressure conditions. The largest autoclaves capable of processing rocket-scale components exist at only a handful of locations worldwide. Each autoclave can process only one major component at a time, with curing cycles measured in days. Expanding composite production requires building new autoclaves, a process requiring 2 to 4 years from groundbreaking to operation. Guidance systems require inertial measurement units containing gyroscopes and accelerometers manufactured to extraordinary precision. The best units can detect rotations of a few thousandths of a degree and accelerations of a few millionths of Earth's gravity. Manufacturing these sensors involves processes so sensitive that some remain classified for national security reasons. The facilities producing navigation-grade inertial units serve military aircraft, submarines, and missiles in addition to rockets. Production capacity cannot be shared freely across these applications. The workforce constraints deserve particular attention because they represent a limit that money cannot quickly solve regardless of how much is available. Space industry workers require combinations of education, training, certification, and experience that take years to develop. A technician who inspects rocket welds must complete 2 to 3 years of general welding training, then 2 to 4 years of specialized aerospace welding certification, then accumulate practical experience under supervision before working independently. The total development time approaches 5 to 7 years for a single skilled worker. An engineer who designs propulsion systems requires 4 years of undergraduate education, then 5 to 10 years of practical experience before achieving the judgment necessary for independent design work. The engineer must understand fluid dynamics, thermodynamics, materials science, structural mechanics, and control systems, then integrate this knowledge into designs that function under conditions no textbook fully describes. This expertise cannot be compressed into shorter timelines, regardless of educational resources deployed. A flight director who manages launch operations represents the accumulation of years of progression through increasingly responsible positions. The director must understand every system on the vehicle and every procedure in the operations manual. More importantly, the director must make split-second decisions during anomalies that no procedure anticipated. This judgment develops only through experience with actual operations, including experiencing problems and learning their solutions firsthand. Confirmed employment data shows that the global space workforce totals approximately 1 million people across all segments, including manufacturing, operations, research, and support. This number includes everyone from janitors at launch facilities to executives at aerospace corporations. Of this total, perhaps 100,000 possess the specialized skills required for rocket production and launch operations. This critical workforce took decades to develop through steady investment in education, training, and retention. It cannot be rapidly expanded regardless of available funding. Training new workers requires existing experienced workers to serve as instructors and mentors. But every hour an experienced technician spends training apprentices is an hour not spent on production tasks. Expanding the workforce requires temporarily reducing production output to invest in training, creating a constraint that operates in the opposite direction from capacity expansion goals. The industry must somehow train more workers while simultaneously increasing production, a contradiction that admits no easy resolution. Expanding facilities requires construction timelines measured in years regardless of budget availability. A new rocket factory must be designed, permitted, constructed, equipped, and commissioned before producing its first component. Environmental reviews alone can consume 12 to 18 months. Construction of a major aerospace facility typically requires 2 to 4 years. Installing specialized equipment and validating production processes adds additional months. A decision to expand production made today cannot yield increased output for 3 to 5 years under optimistic assumptions. Certifying new suppliers requires qualification processes that cannot be accelerated without compromising the safety margins that keep rockets from exploding. A new supplier of critical components must demonstrate manufacturing capability through sample production runs. Those samples must be tested extensively, sometimes to destruction. Production processes must be audited and documented. Quality systems must be verified. The qualification process for a new engine component supplier typically requires 18 to 36 months, even when the supplier has relevant experience from other industries. Every constraint feeds into every other constraint, creating systemic limits on how quickly production can scale. More engines require more trained workers, but training more workers requires diverting existing workers from production. More vehicles require more composite structures, but more composite structures require more autoclave capacity. More launches require more pad infrastructure, but more pad infrastructure requires years of construction. The system as a whole can expand, but only at rates determined by the slowest scaling element. Ground infrastructure presents equally binding constraints that receive less public attention than vehicle manufacturing but prove equally limiting. A launch pad is not simply a platform for rockets, but a complex industrial facility requiring continuous maintenance, extensive preparation between uses, and recovery time after each launch that no engineering can eliminate. The pad itself contains flame trenches designed to redirect exhaust gases away from the vehicle during liftoff. These trenches must withstand temperatures and pressures that destroy ordinary concrete, requiring special refractory linings that degrade with each use. Water deluge systems pour hundreds of thousands of gallons onto the pad during launch, to suppress acoustic energy that would otherwise damage the vehicle through vibration. The pumps, pipes, and nozzles in this system require inspection and maintenance after every use. Propellant loading equipment must handle cryogenic fluids at temperatures low enough to freeze atmospheric moisture into ice on every exposed surface. Seals and gaskets degrade with thermal cycling. Valves require calibration to ensure precise flow rates. Tanks must be inspected for damage and contamination. Electrical interfaces connect the vehicle to ground power, commanding systems and monitoring telemetry through hundreds of individual connections that must each be verified before flight. After a rocket launches, the pad requires refurbishment that cannot be rushed. Flame damage to concrete and steel must be assessed and repaired. Acoustic damage to delicate systems must be identified and corrected. Propellant systems must be purged, cleaned, and recertified for the next loading operation. Electrical connections must be inspected for heat damage. This turnaround process requires days to weeks, depending on pad design and damage sustained during the previous launch. No amount of funding can eliminate the physical time required for these operations. The number of orbital launch pads worldwide totals approximately 30 facilities capable of supporting missions to orbit. This number has grown slowly over decades, as new spacefaring nations constructed facilities and commercial providers built dedicated pads. But the majority of global launch capacity clusters in a few locations constrained by geography and politics. The United States Eastern Range at Cape Canaveral and Kennedy Space Center in Florida provides the primary launch site for American missions. Equatorial location and overwater trajectory to the east make this site ideal for reaching orbits used by most commercial satellites. But Florida's location also exposes the range to hurricanes that force evacuations multiple times per year. The range supports both government and commercial launches, creating competition for limited pad time. The United States Western Range at Vandenberg Space Force Base in California serves missions requiring polar orbits unreachable from Florida. The site offers launch trajectories over open ocean to the south, but limited infrastructure constrains annual launch rates. Only a handful of pads exist, and each serves specific vehicle types with limited flexibility. Baikonur Cosmodrome in Kazakhstan remains the primary launch site for Russian missions, and, until recently, the only location from which crews could reach the International Space Station. Political tensions between Russia and Western nations have complicated access to this facility and introduced uncertainty into launch planning that cascades through mission schedules. Chinese facilities at Jiuquan, Taiyuan, Xichang, and Wenchang support an expanding launch program but remain largely closed to international commercial payloads. The European spaceport at Kourou in French Guiana provides equatorial access for Ariane and Vega vehicles, but serves a limited customer base. Each facility can support only a limited number of launches per year, determined by pad availability, range safety requirements, and workforce capacity. A single pad might support 12 to 20 launches annually under optimal conditions, with experienced crews and reliable vehicles. Reaching higher rates requires building additional pads, training additional personnel, and expanding support infrastructure, all processes requiring years regardless of funding. Range safety creates another hidden constraint that limits how many launches can occur regardless of vehicle and pad availability. Every launch requires closing airspace along the flight path to protect aircraft from potential debris. Maritime authorities must clear sea areas downrange where spent stages or emergency debris might fall. Emergency response teams must be positioned along the trajectory to respond to potential accidents. Coordinating these requirements across multiple government agencies takes time that cannot be compressed. At busy ranges, multiple launches cannot occur on the same day because each requires the same airspace and sea area closures. Weather delays create cascading schedule impacts as missions back up, waiting for clear windows. The range becomes a shared resource where one customer's problems become every customer's delays. Propellant production adds further constraints that rarely receive public attention, but fundamentally limit how many rockets can launch. A single Falcon 9 launch consumes approximately 450,000 kilograms of propellant liquid oxygen and kerosene refined to rocket-grade purity. The Super Heavy booster portion of Starship will consume approximately 3,400,000 kilograms of liquid methane and liquid oxygen per launch. These quantities exceed what casual observers imagine. Liquid oxygen production occurs at air separation. Plants that cool atmospheric air until it liquefies, then separate oxygen from nitrogen through distillation. Global liquid oxygen production capacity is substantial, serving steel manufacturing, medical applications, water treatment, and chemical synthesis in addition to rocket propellant. But rocket launches require oxygen of higher purity than many industrial applications, and propellant-grade production represents a specialized subset of total capacity. Current space launch operations consume only a small fraction of global liquid oxygen production, but the dramatic increases in launch cadence that permanent Moon or Mars presence would require could strain regional production capacity. Constructing new air separation plants requires 2 to 4 years, and capital investments measured in hundreds of millions of dollars. Regional shortages could emerge faster than new capacity could be built, creating bottlenecks invisible to mission planners focused on rocket availability. More exotic propellants face tighter constraints with less flexibility. Liquid hydrogen, used by the Space Launch System, Delta IV, and Ariane rockets, requires specialized production facilities that operate at extremely low temperatures. The infrastructure for producing, storing, and transporting liquid hydrogen exists at only a few locations worldwide, and expanding this infrastructure requires years of construction, plus regulatory approvals for handling hazardous materials. Hypergolic propellants used for spacecraft maneuvering thrusters present even more constrained supply chains. These propellants ignite spontaneously on contact with each other, eliminating the need for ignition systems but requiring extraordinarily careful handling. The chemicals involved are acutely toxic. Manufacturing facilities require extensive safety systems. Transportation regulations limit how much can move through population centers. The specialized facilities producing these propellants cannot rapidly scale production without major capital investment, environmental permitting, and regulatory approval processes spanning years. Launch window limitations compound these industrial challenges for destinations beyond low Earth orbit. The Moon is accessible for landing missions approximately once per month, when the Sun illuminates potential landing sites appropriately. The narrow Mars windows demand even more precise scheduling, with all cargo and vehicles needing to be ready during brief departure opportunities. For lunar operations, missing several consecutive launch windows could leave a base undersupplied for extended periods. Equipment failures between resupply opportunities could cascade into mission-threatening situations. For Mars operations, missing a single launch window means waiting over 2 years for the next opportunity. Cargo already manufactured must be stored and maintained. Perishable supplies may expire. Crews trained for departure must remain proficient during the extended delay. This temporal rigidity means that launch cadence must not merely achieve high average rates, but must reliably deliver specific launches at specific times. A launch program that achieves 50 missions per year provides no help if none of those missions occur during required windows. The industrial system must coordinate vehicle production, payload integration, pad preparation, and propellant supply to hit narrow temporal targets, while simultaneously maintaining ongoing operations. Vehicle manufacturing typically begins 18 to 24 months before planned launch dates. This lead time means that production decisions made today determine launch capabilities 2 years from now. Errors in demand forecasting, supplier problems, or manufacturing defects discovered late in production can create gaps in launch schedules that cannot be filled regardless of subsequent effort. The delay propagates through mission timelines, pushing surface operations further into the future. The COVID-19 pandemic demonstrated supply chain fragility in ways that space planners will study for decades. Supplier deliveries were disrupted when transportation networks operated below capacity. Testing schedules extended when facilities operated with reduced staffing. Launch rates declined temporarily before recovering as conditions improved. A more sustained disruption could have created gaps measured in years rather than months. Climate events increasingly affect launch operations with frequencies that complicate long-term planning. Hurricanes force evacuations of Florida launch facilities multiple times per year, sometimes during critical preparation phases for major missions. Wildfires have threatened California launch complexes, requiring precautionary shutdowns. Extreme temperatures stress ground equipment designed for narrower operating ranges. As climate instability increases, these disruptions will become more frequent, more severe, and more difficult to predict. All of this still fails because launch cadence collapse ultimately traces back to these industrial realities that exist whether acknowledged or ignored. The rocket that lifts off represents years of manufacturing time, compressed into minutes of flight. The engines accumulated thousands of hours of fabrication, testing, and integration. The structures spent months in autoclaves and assembly fixtures. The avionics required years of design, prototyping, and qualification. The entire vehicle embodies the coordinated output of an industrial system operating at maximum sustainable effort. Increasing launch rates requires expanding every element of this industrial base simultaneously. Engine production must increase alongside vehicle assembly. Pad infrastructure must grow alongside propellant supply. Workforce training must accelerate alongside facility construction. Any single element that fails to expand becomes the bottleneck, limiting the entire system. The slowest scaling constraint determines maximum achievable cadence regardless of performance elsewhere. Current cadence barely supports existing operations while leaving minimal margin for the dramatic increases that expansion would require. The industrial system has been optimized over decades for current demand levels. Expanding to meet significantly higher demand requires investment timelines measured in years and faces physical limits that funding alone cannot overcome. But even if industrial capacity somehow expanded to meet requirements for permanent presence beyond Earth orbit, another set of constraints would immediately assert themselves with equal force. Everything in space is decaying. Every satellite, every station, every vehicle begins deteriorating from the moment it leaves Earth's protective atmosphere. Understanding the relentless entropy consuming every orbital asset reveals why launch cadence requirements never decrease. They only grow as infrastructure ages and the orbital environment itself degrades. The vacuum of space appears pristine and eternal. Photographs from orbit show gleaming spacecraft against the velvet backdrop of stars, their surfaces reflecting sunlight with mirror-like brilliance. Videos of rocket boosters landing upright on drone ships suggest a future where vehicles fly again and again like commercial aircraft, accumulating thousands of flights over decades of service. Popular imagination pictures space hardware as permanent infrastructure, built once and operated indefinitely, like bridges or buildings. This appearance deceives completely. The space environment attacks every human-made object through processes that never pause, never relent, and cannot be prevented through any known technology. From the moment any spacecraft leaves Earth's protective atmosphere, degradation begins. Materials weaken, systems fail, components wear out. The countdown toward replacement starts immediately and runs continuously until the asset is abandoned or replaced. Understanding this relentless decay reveals why launch cadence requirements never decrease over time. They only grow as infrastructure ages, as the orbital environment itself degrades, and as the accumulated demands of maintenance compound with each passing year. The dream of building permanent space presence through a finite construction effort, followed by self-sustaining operations, contradicts fundamental physics. Space presence requires continuous industrial commitment that must grow rather than stabilize. Begin with the celebrated achievement of rocket reusability. The the technology most often cited as the solution to space access costs. SpaceX successfully lands and reflights Falcon 9 boosters, dramatically reducing the price of reaching orbit compared to expendable vehicles that splash into the ocean after a single use. This achievement represents genuine progress that has transformed the economics of satellite deployment. Launch costs have decreased substantially, and flight rates have increased beyond what seemed possible a decade ago. But the economics of reuse contain hidden costs that complicate the cadence equation in ways that optimistic presentations rarely acknowledge. Reusability does not eliminate industrial effort. It transforms that effort from manufacturing into refurbishment while introducing new constraints that limit how quickly any reusable fleet can actually fly. A Falcon 9 booster returns from space having experienced forces and environments that would destroy most machines ever built by human hands. The ascent subjects the vehicle to maximum aerodynamic pressure as it accelerates through the thickening lower atmosphere. Vibration from 9 engines operating at full thrust shakes every component and every joint. Acceleration forces compress propellant tanks and stress structural connections. The engines themselves experience combustion pressures approaching 100 atmospheres, while turbopumps spin at speeds that would tear apart ordinary machinery. Then comes the violence of re-entry and landing. Atmospheric re-entry subjects the vehicle to temperatures exceeding 1000 degrees Celsius as air compression converts kinetic energy into heat. The engines must relight in a harsh thermal environment to slow descent. Grid fins actuate through thousands of degrees of motion against aerodynamic loads. The landing legs deploy and absorb impact forces that propagate through the entire structure at touchdown. Each landing represents a controlled crash that would total any automobile. After landing, every booster undergoes extensive inspection and refurbishment before its next flight. This process is not optional and cannot be abbreviated, regardless of schedule pressure. Engines are removed from the vehicle and examined for wear, cracking, or contamination. Turbopump bearings are measured for dimensional changes that indicate fatigue. Combustion chambers are inspected for erosion that could cause failure on subsequent flights. Any component showing wear beyond acceptable limits must be replaced. Tanks are checked for dents, cracks, or delamination that could cause catastrophic failure under pressure. Avionics are tested to verify that vibration and thermal cycling have not degraded circuit boards or connections. Structural components undergo non-destructive examination using ultrasound, X-rays, or other techniques to find cracks invisible to visual inspection. Landing legs are examined for damage from touchdown impacts. Grid fins are checked for warping from aerodynamic heating. This refurbishment process requires weeks of labor by specialized technicians using equipment and facilities dedicated to the task. Confirmed operational data shows that Falcon 9 booster turnaround times average approximately 6 to 8 weeks between flights under normal circumstances. Some boosters have achieved faster turnarounds during periods of exceptional demand, but achieving these compressed schedules requires pulling resources from other activities and cannot be sustained indefinitely. The average turnaround time represents what operations can sustain given available workforce, facilities, and the physical requirements of thorough inspection. Cutting corners risks catastrophic failure. The Challenger and Columbia disasters taught the space industry that schedule pressure leading to inadequate inspection kills crews and destroys programs. No responsible operator will repeat those mistakes regardless of commercial incentives. More critically, boosters do not fly indefinitely, regardless of refurbishment quality. Each reuse accumulates wear that eventually renders vehicles unserviceable. SpaceX has flown individual boosters over 20 times, demonstrating durability that seemed impossible when reusability programs began. But each flight degrades components in ways that inspection cannot fully characterize until failure occurs. Metal fatigue accumulates invisibly with each stress cycle. Microscopic cracks form at grain boundaries, grow with each loading event, and eventually connect into macroscopic failures that occur without warning. The welds joining tank sections to engine mounts experience thermal cycling from cryogenic propellant loading to ambient temperatures, and back again with each flight. Composite materials delaminate internally as resin bonds weaken from repeated stress. Seals and gaskets harden from thermal cycling, eventually losing the flexibility needed to prevent leaks. The company has never publicly disclosed the full refurbishment requirements for highly reused boosters, but industry analysis and engineering principles suggest that extensive overhauls become necessary after approximately 10 to 15 flights. These overhauls involve replacing major components, rebuilding engines, and essentially remanufacturing significant portions of the vehicle. The cost approaches new vehicle construction while extending operational life by diminishing increments as the core structures themselves accumulate fatigue. Eventually, every booster must be retired regardless of accumulated flight experience or refurbishment investment. The airframe itself reaches limits beyond which continued operation becomes unsafe. At that point, all the inspection and maintenance and component replacement cannot prevent failure. The vehicle must be replaced by new manufacturing, returning the system to the industrial capacity constraints that reusability was supposed to overcome. This refurbishment cycle consumes resources that could otherwise support new vehicle production. The technicians who inspect returned boosters cannot simultaneously build new ones. The facilities dedicated to refurbishment cannot be used for initial manufacturing. Reusability that reduces per-launch costs actually creates industrial constraints that limit maximum sustainable cadence in ways not captured by simple cost comparisons. No matter how advanced our reusable systems become, this refurbishment entropy ensures that launch capacity requires continuous industrial effort merely to maintain current levels, never mind expand. Every vehicle eventually wears out. Every component eventually fails inspection. Every fleet eventually requires replacement, as accumulated flight cycles exhaust structural margins. The fleet of available vehicles at any moment represents a dynamic equilibrium between production, use, and retirement that must be continuously managed. This returns us to the fundamental barrier that reusability does not solve. Launch cadence depends on available vehicles, and available vehicles depend on production exceeding retirement. If production equals retirement, fleet size remains constant. If retirement exceeds production, fleet size shrinks and cadence must decrease. Only if production exceeds retirement can cadence grow. Reusability changes the economics of this equation, but does not eliminate its fundamental constraints. Space environments accelerate decay processes to degrees that surprise even experienced engineers. Beyond the Earth's protective atmosphere and magnetic field, conditions exist that no terrestrial environment can replicate. Understanding these conditions reveals why everything in space degrades faster than intuition suggests, and why replacement requirements compound relentlessly. Orbital velocity creates kinetic energy that transforms even microscopic particles into destructive projectiles. Objects in low Earth orbit travel at approximately 7.8 kilometers per second. At this velocity, kinetic energy scales with the square of speed, meaning that orbital debris carries enormous destructive potential regardless of size. A paint fleck traveling at orbital velocity carries the kinetic energy equivalent to a rifle bullet. A millimeter-sized debris fragment can penetrate spacecraft hulls. A centimeter-sized object delivers the destructive force of a hand grenade. Confirmed tracking data from United States Space Command reveals that more than 36,000 debris objects larger than 10 centimeters currently orbit Earth. These objects are large enough to track with ground-based radar and include spent rocket stages, dead satellites, and fragments from collisions and explosions. Any of these tracked objects could completely destroy an operational spacecraft on impact, but the tracked objects represent only the largest debris. Millions of smaller fragments, too small to track with current systems, but large enough to damage or destroy spacecraft, occupy the same orbital regions. Statistical models estimate that over 100 million objects larger than 1 millimeter orbit Earth. These particles remain untracked and untrackable, creating a background hazard that cannot be avoided through maneuvers because their locations are unknown. Every new launch adds to this debris population through multiple mechanisms. Spent upper stages remain in orbit for years or decades before atmospheric drag pulls them down. Payload separation hardware springs, explosive bolts, covers, becomes debris the moment it serves its purpose. Spacecraft operations release particles through thruster firings, solar panel deployments, and normal wear. Even successful missions contribute to the debris environment that threatens subsequent missions. The debris environment creates a feedback loop that threatens launch operations themselves. More launches mean more objects in orbit. More objects mean higher collision probability. Higher collision probability means more spacecraft damage and destruction. More destruction creates more debris fragments that increase collision probability further. The cycle intensifies with each passing year, as accumulated debris compounds faster than natural atmospheric drag removes objects from orbit. The Kesler Syndrome, named after NASA scientist Donald Kesler, who first described it in 1978, represents the theoretical endpoint of this feedback process. A cascade of collisions could generate debris faster than natural orbital decay, removes it, rendering certain orbital regions effectively unusable for generations. Such a cascade would not merely threaten individual spacecraft, but could close entire orbital bands to safe operation, stranding satellites in regions too hazardous to approach for repair or removal. Current debris mitigation efforts slow this process, but cannot reverse trends already established. International guidelines require operators to deorbit spent stages within 25 years of mission completion. Spacecraft are designed to passivate at end of life, venting remaining propellants to prevent explosions. Some operators are testing active debris removal technologies, but these measures address future debris growth while the existing population continues orbiting and accumulating. Even without catastrophic cascades, debris impacts already affect operations in ways that consume launch capacity. The International Space Station performs debris avoidance maneuvers multiple times per year, firing thrusters to shift orbit away from tracked objects predicted to approach too closely. Each maneuver consumes propellant that must be replenished through resupply missions. Each kilogram of propellant burned for debris avoidance requires additional launch capacity for replacement, diverting resources from other purposes. Station crews have sheltered in docked spacecraft during close approaches by debris too recently identified for maneuvers to be planned. These shelter events disrupt research activities and remind everyone aboard that the orbital environment grows more hazardous with each passing year. Windows have been damaged by impacts from untracked particles. Sensors have been degraded. The station's exterior accumulates scars from countless tiny impacts that inspection reveals during spacewalks. Solar radiation creates another constant assault on orbital assets that degrades performance regardless of debris avoidance success. Beyond Earth's atmosphere and magnetic field, the full spectrum of solar output bombards spacecraft surfaces with energy that Earth's environment blocks. Ultraviolet light degrades external materials through photochemical reactions that break molecular bonds. White thermal control surfaces yellow and darken, changing their thermal properties and requiring active temperature management to compensate. Flexible materials become brittle, coatings flake and peel. The pristine appearance of newly launched spacecraft deteriorates within months of exposure. Solar panel efficiency decreases by approximately 1 to 3% per year, as radiation damages the semiconductor structures that convert light to electricity. High-energy particles from solar flares and cosmic rays penetrate photovoltaic cells, creating defects that reduce current output. Over a decade of operation, solar arrays may lose 20 to 30% of their original power output, requiring either larger initial arrays or supplemental power systems to maintain spacecraft function. Thermal cycling between sunlight and shadow stresses every mechanical system on orbiting spacecraft. In low Earth orbit, spacecraft complete one orbit every 90 minutes, experiencing sunrise and sunset 16 times per day. With each cycle, external surfaces swing from approximately 150 degrees Celsius in direct sunlight to minus 150 degrees Celsius in shadow. This 300-degree temperature swing occurs 16 times daily, 365 days per year for the entire operational lifetime of the vehicle. Materials expand and contract with each thermal cycle. Joints flex, seals compress and relax. Fasteners experience micro-movements that can loosen connections over thousands of cycles. Lubricants migrate away from contact surfaces. The accumulated effect of millions of thermal cycles degrades mechanical systems in ways that accelerate with operational age. Confirmed data from the International Space Station demonstrates these degradation processes operating at scales that require continuous corrective action. Solar arrays installed during the station's initial assembly, beginning in 1998, have degraded substantially over 2 decades of operation. Power output declined to levels that threaten station capabilities, requiring the launch of new rollout solar arrays beginning in 2021. Installing these new arrays required 6 spacewalks over multiple years, each involving astronauts working outside the station for 6 to 8 hours while ground teams monitored every movement. The arrays themselves were designed, manufactured, and launched through a process requiring years of preparation. The entire effort consumed launch capacity, crew time, and program resources that could otherwise have supported expansion rather than maintenance. Inside spacecraft, radiation penetrates, shielding to damage electronics and degrade materials with effects that accumulate over operational lifetimes. High-energy particles pass through hull material and interact with semiconductor devices, causing bit flips in memory that corrupt data, latch-up conditions that can destroy circuits, and cumulative damage that eventually causes permanent failure. Computer systems must be designed with redundancy and error correction to tolerate radiation damage during their operational lives. But even hardened systems accumulate damage over years of exposure. The space station has required multiple computer replacements as radiation effects exceeded design margins. Each replacement required designing the new system, manufacturing and testing it, launching it to the station, and installing it through crew activities, a process consuming years and significant resources. Seals and gaskets throughout pressurized spacecraft become brittle as radiation breaks polymer chains. Lubricants break down into components that may contaminate optical surfaces or sensitive equipment. Adhesives weaken. The entire material environment inside long-duration spacecraft degrades in ways that require continuous monitoring and occasional replacement of components never intended to be serviced. This internal decay creates a baseline launch cadence requirement that can never decrease while any station operates. Approximately 2 to 4 metric tons of replacement equipment and consumables must reach the International Space Station every month, regardless of crew activities, research programs, or budget pressures. This requirement has remained roughly constant throughout the station's operational life and will continue until the station is decommissioned. The consumables portion of this requirement includes food for the crew, water processing chemicals, oxygen generation supplies, carbon dioxide scrubbing materials, and waste management consumables. These materials are consumed continuously and cannot be recycled completely. Even with water recycling systems operating at over 90% efficiency, makeup water must be delivered regularly. Even with carbon dioxide scrubbers functioning normally, the lithium hydroxide canisters require replacement. The equipment portion includes computers, communication systems, life support components, scientific instruments, and the thousands of items that degrade or fail through normal operation in the space environment. Every pump eventually wears out. Every fan motor eventually fails. Every seal eventually leaks. The station functions only because replacement parts arrive continuously through resupply missions that demand continuous launch cadence. Extending this analysis to lunar or Mars outposts reveals why cadence requirements grow dramatically with distance from Earth. The International Space Station can receive emergency resupply within days if critical systems fail unexpectedly. If a water recycling pump fails, a replacement can launch from Florida or Kazakhstan within a week under emergency protocols. If food supplies run unexpectedly low, cargo can reach the station within days of the need being identified. A lunar base operates under different constraints. Emergency resupply from Earth requires approximately 3 to 4 days minimum transit time, assuming a vehicle is available and ready for immediate launch. More realistically, emergency response would require 1 to 2 weeks from identifying the need to delivering supplies. This timeline requires maintaining larger reserves of critical items to bridge the gap between failure and replacement. A Mars base exists beyond any possibility of emergency resupply within relevant timeframes. Everything needed to survive until the next scheduled resupply, which cannot arrive for nearly 2 years after the supply window opens, must already be present on Mars before any emergency occurs. This extended supply line requires that Mars outposts maintain reserves of everything at levels that would seem excessive for Earth orbital operations. Food supplies must cover not 6 months but over 2 years. Spare parts must include replacements for any system whose failure would threaten crew survival. Medical supplies must address any emergency that might occur during a 3-year mission without the possibility of evacuation. Establishing these reserves requires massive initial launch campaigns that deliver supplies before crews arrive. Maintaining the reserves requires continuous replenishment through every available launch window to replace items consumed during the previous cycle. The safety margins necessary for crew survival at Mars distance multiply cadence requirements by factors of 3 to 5, compared to destinations where emergency resupply remains possible. Human factors add another layer of cadence requirements that technical analyses often minimize or ignore. Astronauts are biological systems subject to degradation in space environments, just as mechanical systems are. But unlike mechanical systems, astronauts cannot be indefinitely repaired or replaced with upgraded components. Human physiology imposes absolute limits on space exposure that drive mandatory crew rotation schedules regardless of other mission requirements. Bone density decreases at approximately 1 to 2% per month in microgravity, despite exercise countermeasures that consume 2 to 3 hours of crew time daily. This loss occurs because bones adapt to loading conditions. Without gravity providing constant loads, the body reduces bone mass as metabolically expensive tissue serving no apparent purpose. Extended missions risk fractures upon return to gravity that could be permanently disabling. Fluid shifts in the absence of gravity move blood and other fluids toward the head, causing facial puffiness visible in astronaut photographs. More seriously, increased intracranial pressure affects the optic nerve and eye structure, causing vision changes that may be permanent. Many long-duration astronauts require corrective lenses after missions who did not need them before. Immune function degrades during spaceflight through mechanisms not fully understood. Dormant viruses reactivate at higher rates than on Earth. Wound healing slows. The ability to fight infection decreases. These changes create medical vulnerabilities that grow with mission duration and cannot be fully prevented through any known countermeasures. Confirmed medical data from long-duration International Space Station crews shows that most physiological effects stabilize or partially recover after approximately 4 to 6 months, but effects continue progressing beyond that point, at rates that increase health risks significantly. NASA currently limits station missions to approximately 6 months for most astronauts, with rare exceptions extending to 1 year only for specific research purposes, with extensive monitoring. These limits create mandatory crew rotation schedules that cannot be deferred regardless of budget constraints or schedule pressures. Every 6 months, new crews must launch to replace returning astronauts who have reached exposure limits. Each rotation requires crew transport vehicles capable of carrying 3 to 4 passengers. Launch capacity dedicated to crew transfer, landing and recovery infrastructure to receive returning astronauts, and extensive training programs for replacement personnel. Missing scheduled rotations means either extending crew exposure beyond medically safe limits or abandoning stations entirely when current crews must return. Neither option is acceptable for sustained operations. The rotation schedule, therefore, creates a baseline launch cadence requirement independent of all other mission needs, a requirement that cannot be reduced through efficiency improvements or technological advances. For lunar operations, crew rotation schedules might potentially extend to 1 year, given lower radiation exposure than deep space transit and the partial gravity of the lunar surface that may reduce some physiological deconditioning. Even with extended rotations, regular crew transfer flights remain mandatory. The Gateway station, planned to orbit the Moon, anticipates crew visits lasting approximately 1 to 3 months, with the station operating uncrewed between visits to reduce exposure requirements. For Mars operations, crew rotations within single mission windows become physically impossible due to transit times and surface stay requirements. Mars mission architectures, therefore, propose surface stays of 18 months or more, with total mission durations approaching 3 years from Earth departure to Earth return. These extended durations push human physiological limits far beyond current experience. The longest Apollo mission lasted approximately 12 days, the entirety of human deep space experience. The medical effects of 3-year missions remain unknown and may prove more severe than models predict. Medical emergencies create another cadence dependency that mission planners acknowledge only reluctantly. An astronaut experiencing appendicitis, traumatic injury, cardiac events, or other serious medical conditions requires capabilities that no spacecraft or space station can fully provide. The definitive treatment for many emergencies is evacuation to Earth-based medical facilities with surgical capabilities, imaging equipment, and specialist physicians unavailable in space. For the International Space Station, evacuation capability exists continuously. Crew transport vehicles remain docked at all times, enabling emergency return to Earth within hours of any medical crisis. This capability provides a safety margin that enables operations with acceptable risk levels, despite the impossibility of comprehensive medical facilities in orbit. For lunar bases, emergency return could potentially be accomplished within days to a week, if vehicles remain available and fueled for immediate departure. This extended timeline requires maintaining medical capabilities on the lunar surface, beyond basic first aid capabilities that themselves require launch cadence to establish and maintain. For Mars bases, no emergency return capability exists within any time frame relevant to acute medical emergencies. A heart attack on Mars cannot be addressed by evacuation. Emergency surgery must be performed by whoever is present with whatever equipment was delivered by previous launches. Medical emergencies that would be survivable with Earth hospital care may prove fatal on Mars despite all preparation. This reality fundamentally limits the crew sizes and mission durations that can be responsibly attempted. Larger crews increase the statistical probability of medical emergencies during any mission. Longer missions increase cumulative exposure to that probability. The acceptable risk envelope constrains Mars operations to small crews, accepting risks that no other human endeavor would tolerate. The decay processes affecting every component of space operations, vehicles, stations, orbital environments, and the human crews themselves create cadence requirements that grow over time rather than diminishing. The optimistic vision of building infrastructure that then operates indefinitely contradicts physical reality at every level. Launch capacity must expand merely to maintain existing capabilities, as depreciation consumes assets. Stations degrade and require continuous resupply. The orbital debris environment worsens and requires more avoidance maneuvers. Human crews rotate and require continuous transportation. Each requirement demands launch cadence. Each requirement grows rather than shrinks with operational duration. Building space infrastructure requires launch cadence to deliver initial construction mass. Maintaining space infrastructure requires ongoing cadence to replace worn and damaged components. Expanding space infrastructure requires additional cadence beyond maintenance levels. The arithmetic points in only one direction toward ever-increasing demands on a launch system that faces absolute physical and industrial limits. The degradation of everything in space means that permanent human presence requires permanent industrial commitment from Earth. Not a burst of construction followed by self-sustaining operations, but continuous manufacturing, continuous launches, and continuous resupply extending as long as any presence is desired to continue. The romantic vision of settlers heading out to build new worlds, independent of Earth, confronts the harsh reality that independence from Earth's supply means death when systems fail. Understanding what these requirements actually total when calculated honestly for destinations beyond the Moon reveals why the mathematics becomes impossible. They exceed what any imaginable expansion of those capabilities could achieve within constraints imposed by physics, industry, and human biology. Every calculation converges on the same conclusion. Strip away the optimistic projections that populate press releases. Discard the aspirational timelines that excite investors and inspire children. Ignore the glossy presentations that assume away the hardest problems while dwelling on the easiest ones. When you honestly account for what permanent human presence beyond the Moon actually requires when you add every kilogram, count every launch, sum every industrial commitment, the numbers exceed what any civilization can sustain. This is not pessimism, this is arithmetic. The mathematics of orbital mechanics, the physics of rocket propulsion, the realities of industrial production, and the constraints of human biology combine into equations that admit no solutions compatible with permanent expansion. Understanding these equations does not diminish human achievement. It clarifies what achievements remain possible, and which dreams must remain dreams. Begin with a minimal Mars base supporting 6 crew members for continuous operations. This represents the smallest viable permanent presence. Barely enough personnel to maintain critical systems, conduct meaningful research, respond to emergencies, and provide the social interaction necessary for psychological health during multi-year isolation. 6 people is not a colony. 6 people is a research station operating at the edge of sustainability. Confirmed NASA analyses developed over decades of Mars mission planning suggest that supporting 6 people on Mars requires approximately 15,000 kilograms of consumables per year. This mass includes food to provide adequate nutrition, water processing chemicals to maintain recycling systems, medical supplies for routine care and emergency response, carbon dioxide scrubbing materials, oxygen generation consumables, and the countless small items that sustain biological existence in an environment actively hostile to life. 15,000 kilograms sounds manageable until you consider what it represents. This mass equals approximately 8 fully loaded passenger automobiles arriving at Mars every year just to keep 6 people alive, not thriving, not expanding, not building civilization, simply surviving for another year while consuming the accumulated output of Earth's industrial capacity. But consumables represent only the beginning of the accounting that Mars presence requires. Equipment, replacement for a Mars surface habitat, creates demands that grow rather than diminish over operational years. Solar arrays degrade from the constant accumulation of Martian dust and the relentless assault of radiation unfiltered by any meaningful atmosphere. Battery systems lose capacity with each charge-discharge cycle until they can no longer store sufficient energy for nighttime operations. Air processing equipment wears out as pumps fail, filters clog, and seals deteriorate in the corrosive Martian environment. Water recycling systems require continuous maintenance as membranes foul, catalysts degrade, and mechanical components fatigue from constant operation. Thermal control systems fight the extreme temperature swings between Martian day and night, accumulating wear that eventually exceeds repair capability. Communication systems, navigation equipment, scientific instruments, and the dozens of subsystems that a functioning habitat requires each have limited operational lifetimes that replacement must address. Confirmed experience from the International Space Station suggests that equipment replacement mass approaches or exceeds consumable mass for long-duration operations in hostile environments. The station, operating in comparatively benign low Earth orbit with emergency resupply available within days, requires continuous delivery of replacement components to maintain functionality. Mars operations, facing harsher conditions with no possibility of emergency support, would require even more extensive replacement inventories. Add vehicles to the accounting that honest Mars assessment requires. A minimal Mars presence requires surface transportation for exploration beyond walking distance and for emergency evacuation if primary habitats fail. Pressurized rovers, with life support systems capable of multi-day excursions, weigh thousands of kilograms each and require their own maintenance, consumables, and eventual replacement. Unpressurized utility vehicles for cargo transport and local operations add additional mass requirements. Ascent vehicles for crew return must remain fueled and operational throughout surface, stays lasting 18 months or longer. These vehicles cannot be used for any other purpose while serving as the only escape route from Mars. Their propellants must be maintained at required temperatures and pressures. Redundant vehicles may be necessary to ensure crew safety if primary systems fail. Orbital assets for communication relay and transit support require their own maintenance and resupply, independent of surface operations. Communication satellites enabling contact with Earth must remain operational throughout mission durations. Transit vehicles waiting in Mars orbit to return crews to Earth require station-keeping propellant, thermal management, and system maintenance during the long months between crew arrival and departure. Conservative estimates that account for all these requirements suggest that sustaining 6 people on Mars continuously requires delivering approximately 50,000 to 100,000 kilograms to the Martian surface per year once initial infrastructure exists. This estimate generously assumes substantial in-situ resource utilization for water extraction and perhaps propellant production, reducing but never eliminating dependence on Earth supply. The lower bound of 50,000 kilograms assumes that water extraction from Martian ice operates flawlessly, that propellant production from atmospheric carbon dioxide achieves design efficiency, and that no major equipment failures require unplanned replacement. These assumptions may prove optimistic. The upper bound of 100,000 kilograms assumes more conservative performance from local resource utilization and provides margins for the inevitable equipment failures that operations in unexplored environments encounter. Convert these surface mass requirements to Earth launch requirements, and the scale of industrial commitment becomes apparent. Every kilogram delivered to the Martian surface requires approximately 7 to 10 kilograms launched from Earth's surface when properly accounting for all mission phases. Transit propellant to escape Earth's gravity and travel to Mars consumes mass. Propellant for course corrections during the 7 to 9 month journey adds more. Mars orbital insertion burns require additional propellant. Entry, descent, and landing systems that protect cargo through atmospheric friction and deliver it safely to the surface add substantial mass that does not reach the surface itself. Using the conservative ratio of 7 to 1, delivering 50,000 kilograms to Mars annually requires launching approximately 350,000 kilograms from Earth each year. Using current heavy-lift vehicles capable of placing 20 to 30,000 kilograms in low Earth orbit per launch, this delivery requirement translates to 12 to 18 heavy launches per year, dedicated solely to Mars surface support. 12 to 18 heavy launches annually sounds achievable given current global capacity exceeding 200 total orbital launches per year, but these launches must occur during the brief windows when orbital geometry permits efficient transfers. Missing a window means waiting over 2 years for the next opportunity, while surface crews consume reserves at rates that cannot be reduced regardless of supply delays. Concentrating a year's worth of Mars cargo into launches occurring within a few weeks creates surge requirements that steady-state capacity cannot address. Launch pads, vehicle manufacturing, payload integration, and workforce availability must align simultaneously during narrow temporal windows. Any disruption, weather delays, vehicle anomalies, supply chain problems cascades through tightly scheduled launch campaigns with consequences measured in years of delayed supply. But this minimal scenario, examining only surface support ignores the extensive infrastructure required to enable those Mars deliveries. No mission architecture proposed by any space agency sends cargo directly from Earth's surface to Mars landing sites. Every serious Mars architecture requires orbital assembly, staging, and refueling operations that demand their own continuous launch cadence independent of Mars surface requirements. Transit vehicles for Mars missions exceed the payload capacity of any existing or planned launch vehicle. And life support systems for a Mars transit vehicle total hundreds of thousands of kilograms that must be assembled in orbit from components delivered by multiple launches. This assembly requires dedicated orbital facilities, crew transport for construction operations, and propellant depots for fueling assembled vehicles. Each supporting element requires its own launch cadence, extending years before any Mars mission departs. Propellant depots must be delivered, tested, and filled. Crew rotation for orbital construction workers demands regular transport flights. The infrastructure to enable Mars missions requires launch cadence before, during, and after any specific Mars expedition. Confirmed NASA architectures for Mars missions propose lunar orbital stations as staging points, reducing the energy requirements for Mars departure by using the Moon's gravitational position. The Gateway Station planned for lunar orbit would serve as a waypoint for Mars-bound crews and a testbed for technologies required for longer journeys. But Gateway itself requires approximately one resupply mission per year, plus periodic crew rotations lasting 1 to 3 months each. Lunar surface operations supporting Mars preparation would require additional launches beyond Gateway support. Testing equipment, developing resource utilization techniques, and building experience with surface operations in environments closer to Earth than Mars, but more challenging than the space station demands, regular cargo deliveries, crew rotations, and infrastructure maintenance. Each lunar mission that supports eventual Mars capability requires its own launch from Earth. Earth orbital infrastructure for transit vehicle assembly and fueling requires construction, maintenance, and continuous support launches. Propellant delivery to orbital depots must occur regularly to maintain reserves for mission fueling. Communication satellite upgrades to support deep space operations add further launch requirements. Adding these infrastructure requirements to direct Mars surface support, maintaining a minimal Mars presence with the lunar and orbital systems needed to enable it, requires approximately 50 to 100 Earth launches per year across all vehicle types. This number represents a substantial fraction of current global launch capacity, while assuming that no other launch requirements compete for the same rockets, pads, workforce, and industrial resources. This brings us back to the fundamental barrier that underlies every honest assessment of human space expansion. Current requirements do not disappear. When Mars operations begin, communication satellite constellations require regular replacement launches as aging spacecraft reach end of life. Military and intelligence satellites that governments consider essential for national security demand continued access to orbital launch services. Scientific missions exploring other destinations in the solar system compete for launch slots that cannot be infinitely multiplied. Commercial satellite services continue growing as global demand for communications, imaging, and navigation expands. The industrial base supporting current launches cannot simultaneously support current requirements, plus dramatic Mars expansion, plus lunar infrastructure, plus orbital assembly operations. Workforce limitations prevent rapid scaling of rocket production, regardless of funding. Pad availability constrains launch rates regardless of vehicle manufacturing capacity. Supply chains for specialized components face their own capacity limits independent of demand signals. The arithmetic does not balance. Current capacity cannot accommodate current requirements plus expansion requirements. Expanding capacity requires years of investment that must be sustained continuously. Any interruption in that investment leaves capacity inadequate for the operations it was intended to support. This brings us back to the fundamental barrier that no technology resolves. Launch cadence collapse is not a failure of current systems awaiting better engineering. It is an inherent limitation of any system requiring continuous material supply from Earth's surface to destinations where local resources cannot substitute for Earth-manufactured goods. The physics of rocket propulsion ensures that every kilogram reaching distant destinations requires multiple kilograms launched from Earth. The complexity of modern manufacturing ensures that rockets cannot be produced faster than industrial processes allow, regardless of demand. The constraints of specialized workforce development ensure that trained personnel cannot be created faster than experience accumulates. The requirements of physical infrastructure ensure that launch pads, assembly facilities, and support systems cannot be built faster than construction timelines permit. These constraints combine into absolute limits on how many rockets can launch per year. Those limits determine how much mass can reach orbit. Mass in orbit determines how much can transfer toward distant destinations. Mass at destinations determines how many people can be supported and for how long. The chain of dependencies admits no shortcuts. Each link constrains the next. The weakest link determines system capacity regardless of strength elsewhere. Speculative technologies often proposed as solutions to launch constraints fail under honest analysis to address the cadence fundamentals that determine expansion feasibility. Space elevators would reduce energy requirements for reaching orbit by replacing rocket propulsion with mechanical climbing along cables extending from Earth's surface to geostationary orbit. This concept has attracted serious engineering study for decades, but space elevators require materials with strength-to-weight ratios that no known substance achieves. Carbon nanotubes theoretically possess adequate strength, but manufacturing defect-free nanotube cables, 60,000 kilometers long, remains beyond current or near-term capability. Even optimistic projections place operational space elevators decades in the future, after development efforts costing hundreds of billions of dollars. More critically, space elevators would create their own maintenance cadence requirements while remaining vulnerable to failure modes that rockets avoid. Climber vehicles ascending the cable would require manufacturing and maintenance. The cable itself would require continuous monitoring and repair, as micrometeorite impacts accumulate damage over operational years. Station-keeping systems at the geostationary anchor point would require propellant and replacement. A space elevator is not a permanent structure, but a continuous operation requiring industrial support throughout its existence. Orbital debris impacts present existential threats to any space elevator. A cable extending through thousands of kilometers of orbital space intersects debris-populated regions where even small particles carry destructive energy. A single cable severance at any point destroys the entire system, requiring reconstruction efforts spanning years. The debris environment that current launch operations are worsening makes space elevator viability increasingly questionable regardless of materials development. Nuclear thermal propulsion improves specific impulse compared to chemical rockets, meaning that each kilogram of propellant produces more velocity change. This improvement reduces propellant mass requirements for any given mission, potentially reducing the number of launches needed to support Mars operations. Nuclear thermal engines have been tested successfully, and modern designs offer performance approximately double that of the best chemical engines. But propellant mass represents only one constraint among many determining launch cadence. Nuclear engines still require manufacturing through industrial processes with their own scaling limits. The specialized materials, precision components, and radiation-hardened systems in nuclear propulsion stages demand workforce expertise and facility capabilities that face the same expansion constraints as chemical rocket production. Building more nuclear stages requires expanding the industrial base, training additional workers, and constructing new facilities through processes requiring years, regardless of funding. Launch pads, payload integration facilities, mission control infrastructure, and supply chains for non-propulsion components face identical constraints regardless of what propulsion technology vehicles use. Nuclear thermal propulsion might reduce the number of launches needed by 30 or 40% as a meaningful improvement, but cannot reduce requirements by the factors of 5 or 10 needed to bring Mars operations within sustainable 5 cadence limits. In situ resource utilization on the Moon or Mars offers the most promising path toward reducing Earth launch requirements. If water can be extracted from lunar ice or Martian permafrost, crews need not launch water from Earth's deep gravity well. If propellant can be manufactured from Martian atmospheric carbon dioxide and extracted water, local resources substituting for Earth-supplied materials reduce the mass that launch cadence must deliver, but establishing resource utilization facilities requires substantial initial mass delivered from Earth before any local production begins. Mining equipment, processing plants, power systems, storage facilities, and the infrastructure supporting these operations must be manufactured on Earth, launched into space, transported to destination, and assembled before producing their first useful output. The bootstrap problem cannot be solved without sustained launch cadence during the years-long development period. Operating resource utilization facilities requires equipment manufactured on Earth until local manufacturing capabilities develop capabilities that themselves require additional infrastructure launched from Earth. Replacement parts for mining equipment must come from Earth until machine shops capable of fabricating replacements exist on Mars. Those machine shops require their own equipment launched from Earth. The recursion continues until capabilities exist that current technology cannot provide at any destination beyond Earth. Advanced manufacturing using three-dimensional printing and local materials might eventually enable production of some components at off-Earth locations. Closed-loop life support systems might eventually reduce consumable requirements toward theoretical minimums, but achieving reliable performance from these systems requires technology development that itself demands continuous launch support for testing, iteration, and refinement over years or decades. No space habitat has achieved full closure of life support loops despite decades of research in orbital facilities. The International Space Station recycles approximately 90% of water, an impressive achievement, but requires continuous resupply of the remaining 10%, plus replacement of recycling equipment that degrades during operation. Mars facilities might achieve higher closure rates, but assuming perfect performance from untested systems operating in unexplored environments contradicts all engineering experience. Every proposed solution eventually traces back to the same fundamental requirement. Reaching a sustainable off-Earth presence requires passing through a period of high launch cadence to establish infrastructure, develop capabilities, and achieve self-sufficiency that may or may not prove attainable. This period stretches years to decades depending on the destination and desired capability level. Throughout this entire period, industrial capacity must support cadence requirements exceeding anything currently achieved while maintaining existing operations that cannot be abandoned. Confirmed, historical data shows that global launch cadence has fluctuated between approximately 50 and 200 launches per year over the past half-century. The recent increase toward 200 launches per year represents exceptional circumstances unlikely to be sustained indefinitely. SpaceX's reusable rocket systems matured simultaneously with explosive growth in commercial satellite constellations and expanded Chinese space activities. These drivers converged to produce current launch rates that significantly exceed historical averages. Sustaining 200 launches per year, while adding the 50 to 100 additional launches required for minimal Mars operations, would require increasing global launch capacity by 25 to 50% from current levels. This increase would require proportional growth in rocket manufacturing facilities, engine production lines, launch pad infrastructure, propellant production capacity, workforce training programs, and supply chain capabilities for thousands of specialized components. Historical industrial scaling from comparable technology sectors suggests that increasing manufacturing capacity by 50% requires approximately 3 to 7 years of sustained investment, even with effectively unlimited funding. Workforce training cannot be accelerated beyond rates determined by apprenticeship requirements and experience accumulation. Supply chains for specialized components face their own expansion constraints independent of customer demand. During the years required for capacity expansion, current operations must continue without interruption. The industrial system must simultaneously maintain existing capability, serve existing customers, and build toward expanded future capability. Any resources diverted to expansion reduce availability for current operations. The transition period creates maximum stress on systems already operating near capacity limits. More critically, increasing capacity creates industrial commitments that must be sustained indefinitely once established. A workforce trained and employed for 300 launches per year cannot be instantly reduced if demand declines. Facilities built and staffed for expanded production represent fixed costs that persist regardless of utilization. Supply chains scaled for higher volumes require minimum orders to remain viable. The path to sustained Mars presence requires committing industrial resources for decades at scales significantly exceeding current capacity. This commitment must begin years before any Mars capability becomes operational and must continue indefinitely thereafter. Any interruption in this commitment, economic recession, reducing available investment, political change, redirecting priorities, natural disaster disrupting supply chains, a pandemic halting workforce availability collapses the cadence on which permanent presence depends. Examine the historical record for evidence that such commitments can be maintained across the timescales Mars permanence would require. The Apollo program achieved launch cadence sufficient for lunar landing missions through a national effort consuming approximately 4% of federal budget at peak. But that commitment could not be sustained beyond a few years, despite successful missions and public enthusiasm. Political and economic priorities shifted. Funding declined. Production lines closed. The industrial capability that reached the moon dissipated within a decade of the first landing, leaving only memories and museum exhibits. The Space Shuttle program maintained operational cadence for 30 years, demonstrating that long-duration commitments remain possible. But the shuttle achieved roughly 4 to 5 launches per year, rather than the 50 originally projected when the program began. Even this dramatically reduced tempo strained NASA's resources, workforce capacity, and institutional attention. 2 catastrophic accidents, killing 14 astronauts, resulted from pressures created by cadence requirements that exceeded sustainable operational tempos. The program's history demonstrates both the possibility of sustained commitment and the consequences when commitment exceeds capability. The International Space Station has sustained operations for over 2 decades, through international partnership, distributing costs and responsibilities across multiple nations. This cooperation has proven remarkably resilient, despite geopolitical tensions that might have ended purely national programs. But total station support represents modest cadence requirements compared to Mars expansion. The station houses 6 people in low Earth orbit, the closest and easiest destination. Supporting 6 people on Mars requires effort greater by factors that transform the problem qualitatively rather than merely quantitatively. No historical precedent exists for the sustained industrial commitment that permanent Mars presence would require. No civilization has maintained technical infrastructure at peak capacity for decades without interruption. No political system has sustained focused investment in single programs across multiple leadership transitions and shifting priorities. No economy has allocated resources to individual endeavors at the scales required while maintaining other essential functions. The philosophical implications of this arithmetic deserve acknowledgement, even in analysis focused primarily on physical constraints. Humans evolved as a species that expanded continuously across Earth's surface over hundreds of thousands of years. Every continent except Antarctica hosts permanent human presence, established through migration and adaptation. The intuition that expansion represents human nature runs deep in consciousness and culture. But terrestrial expansion occurred across surfaces connected by atmosphere and water where humans could breathe without technological intervention. Resources required for survival, food, water, materials for shelter existed at destinations awaiting only human ingenuity to exploit. Technology for transportation developed incrementally, from walking to rafts to sailing ships to aircraft, each advance building on accumulated experience. No fundamental physical barriers prevented continuous expansion once initial capabilities existed. Space expansion violates every assumption underlying terrestrial experience. No resources for survival exist at any destination beyond Earth without continuous supply from home. The Moon contains no air, no liquid water, no food, no fuel. Mars contains thin, toxic atmosphere, frozen water requiring extraction, no organic materials, no manufactured goods. Everything necessary for human survival must be delivered from Earth, or produced using equipment delivered from Earth. Transportation beyond Earth requires energy expenditure dwarfing anything terrestrial expansion encountered. Crossing oceans required favorable winds and accumulated sailing knowledge. Reaching orbit requires accelerating to velocities 11 times faster than rifle bullets, while carrying everything needed for survival. The energy differential between terrestrial and space transportation spans factors of thousands, transforming human expansion from a challenging undertaking to a physical impossibility under current constraints. No incremental path connects current capabilities to self-sustaining presence beyond Earth. Terrestrial expansion proceeded through gradual extension of existing capabilities. Longer voyages, better ships, improved navigation. Space expansion requires revolutionary capabilities that do not exist. Closed-loop life support that no system has achieved. Local manufacturing that requires industrial infrastructure. Resource extraction that remains unproven at necessary scales. The gap between current capabilities and required capabilities cannot be crossed through incremental improvement over human-relevant timescales. The barrier confronting space expansion is not technological inadequacy, awaiting better engineering. The barrier is physical reality, embedded in the nature of propulsion, distance, and industrial capacity. The rocket equation ensures that reaching distant destinations requires enormous mass expenditure that cleverness cannot eliminate. The nature of space environments ensures that everything degrades continuously, regardless of design quality. The complexity of life support ensures that independence from Earth requires capabilities that may not be achievable through any conceivable development path. This does not mean humans cannot visit the Moon or Mars. Apollo demonstrated conclusively that lunar visits remain within human capability given sufficient commitment. Current technology could certainly deliver crews to Mars for exploratory missions lasting months or years. The engineering challenges are substantial, but not insurmountable for expeditionary goals. But visits are not presents. Expeditions are not settlements. Flags and footprints are not civilizations. The distinction matters because permanence requires solving problems that visits avoid entirely. A lunar expedition can accept equipment that functions for months. A lunar settlement requires equipment that functions for decades with continuous replacement. A Mars expedition can accept risks that would be unacceptable for permanent presence. A Mars settlement must achieve safety margins sustainable across generations. Without continuous launch cadence at scales, no civilization has demonstrated capacity to sustain. A permanent expansion beyond the Moon collapses inevitably. Initial infrastructure decays through processes that cannot be prevented. Supplies exhaust at rates that cannot be reduced below biological and physical minimums. Equipment fails according to reliability statistics that accumulate towards certainty over operational years. Crews either return to Earth before consumables exhaust, or perish when return becomes impossible and supplies end. The investments of decades dissipate into abandoned hardware and fading memories. Habitats constructed through thousands of launches fall silent as their systems fail without replacement. Equipment representing billions of dollars and millions of working hours degrades into functionless artifacts. The brief presence that enormous effort established disappears as if it never existed, leaving only records of what was attempted and why it could not be sustained. The honest assessment of human space futures must begin with these physical realities rather than aspirational visions that assume them away. Dreams of Mars colonies, asteroid settlements, and interstellar expansion cannot be evaluated meaningfully without confronting the launch cadence requirements they would create. Those requirements exist whether acknowledged in planning documents or ignored in inspirational speeches. Physics does not negotiate. Industrial capacity does not expand by decree. Perhaps future developments will change this arithmetic in ways current analysis cannot anticipate. Perhaps breakthrough propulsion technologies will reduce mass penalties to levels that make expansion feasible. Perhaps human determination will achieve outcomes that honest analysis concludes are impossible. But hoping for breakthroughs is not planning. Assuming capabilities that do not exist is not engineering. Basing expansion programs on technologies that might be invented contradicts every principle of responsible program management. The systems that could sustain permanent human presence beyond the moon remain conceptual. The launch cadence that permanence requires remains unachievable with any existing or firmly planned capability. The industrial commitments necessary remain unprecedented in human experience. Every rocket that leaves Earth's surface carries with it the accumulated effort of thousands of workers, millions of manufacturing hours, and billions of dollars in infrastructure investment. Sustaining cadence sufficient for Mars presence would require multiplying these commitments by factors that no existing or credibly planned system achieves. The multiplication required exceeds not just current capacity, but plausible expansion of that capacity within timeframes relevant to human planning. The stars will remain in the sky, beautiful and unreachable. The moon will continue its ancient orbit, close enough for visits, but not for permanent habitation, without commitment that history suggests cannot be maintained. Mars will gleam red in the evening sky, inviting dreams that physics does not permit to become reality. And humans will continue imagining futures among these destinations, as our species has imagined since first looking upward and wondering what lies beyond. But between dream and reality lies an industrial chasm that current civilization cannot bridge. The chasm is not one of ambition or courage or imagination. It is one of physics and manufacturing capacity, and the limits of industrial systems that cannot scale beyond constraints imposed by physical reality. No amount of wanting crosses a chasm that exists in the material world rather than the human mind. Launch cadence collapse is not a future threat, requiring vigilance to prevent. It is a present constraint shaping every space program on Earth today. It limits every ambitious plan. It determines every feasible architecture. It forces every honest assessment to conclude that permanent human presence beyond the moon remains beyond human capability. As that capability currently exists and as realistic projections suggest it might develop, until this constraint lifts if it ever can. Through developments not yet imagined, permanent expansion beyond the moon remains impossible. Not difficult, not expensive, not merely challenging. Impossible in the precise meaning of that word. Not capable of being done regardless of effort or resources committed to the attempt. We are not a species destined for the stars by any cosmic plan. We are a species that reached the moon briefly at the peak of industrial and political commitment that could not be sustained. The universe does not oppose human ambition. It simply remains indifferent to ambitions that physical law does not accommodate. This truth is difficult but ultimately necessary. Understanding constraints enables realistic planning toward achievable goals. Accepting limits allows meaningful achievement within those boundaries rather than futile, straining against barriers that cannot yield. The impossible should not distract from the achievable. Permanent expansion beyond the moon may be impossible, but continued scientific exploration, robotic presence on distant worlds, and occasional human visits to nearby destinations remain within reach. The universe has revealed its rules through centuries of accumulated scientific understanding. They are not rules humanity would choose. They are rules that constrain dreams and limit ambitions and force acceptance of boundaries that imagination refuses to acknowledge. But they are the only rules that exist, and they are the rules we must respect if our ambitions are to achieve anything lasting, rather than dissipating into frustrated effort and abandoned projects. Launch cadence is the bottleneck through which all space ambitions must pass. It cannot be wished away through optimistic projections. It cannot be assumed away through plans that ignore industrial constraints. It can only be understood, respected, and accepted as the determining factor in what humanity can achieve beyond our home planet. And in understanding it, we understand our place in the cosmos more clearly than any optimistic vision has ever permitted. We are creatures of Earth, bound to our planet by physics that no determination can overcome. The moon remains close enough for visits that commitment might sustain. Everything beyond recedes into impossibility, not because we lack courage or vision, but because the universe does not negotiate with species whose ambitions exceed what physical law allows.